Hello everyone, I'm Eleonora Bianchi, working at the Origins Excellence Cluster. I would like to apologize for not being present and thank the organizer for giving me the opportunity to talk about astrochemistry and in particular complex carbon species. So the formation of planetary systems like our solar system, it's a complex process involving several evolutionary steps. All these different evolutionary steps correspond to an increasing complexity of the gas chemical composition. Astrochemistry is a powerful tool to follow this journey, and if you want to study the chemical complexity available for planets formation, we need to investigate the early stages where the chemical complexity is built up, so in particular the prestellar and protostellar phases. The project I will present is a part of a community observational effort aimed at exploring the chemical content of solar type star-forming regions in different wavelengths. I report here some observational programs in which I had the chance to be involved. So, for example, in the submillimeter, the ASI survey, astrochemical survey at IRAM 30 meter, and the SOLIS large program, Seeds of Life in Space with the NOEMA interferometer. And the most recent ALMA large program FAUS, which is 50 AU study of the chemistry in the disk envelope systems of solar-like protostars. And now we are focusing on radio wavelengths, and I will explain you why we need longer wavelengths. And in this context, I will present you a pilot survey performed with the Green Bank telescope that will pave the way for the future observations with SKA and ngVLA. So when we observe solar type star-forming regions, we see two different types of chemistry, sometimes coexisting in the same source. The so-called hot Corino chemistry, rich of oxygen-bearing species and interstellar complex organic molecules, and the warm carbon chain chemistry, where we have unsaturated hydrocarbons and carbon chains. One hypothesis for the origin of this difference is the different collapse timescale, which could favor chemical reactions starting in one case from CO and in the other from CH4. Alternatively, the CO photodissociation could play a role and lead to a large amount of methane ice. In any case, we need more observations to clarify the origins of this chemical diversity and to explore the complex carbon species reservoir, which is so far mainly unknown. So why do we need lower frequencies to observe these species? There are two main reasons. The first one is that in the submillimeter, we have a huge problem with dust opacity. Here you can see two famous examples. The first one is a binary system, IRAS4A, and when we observe it with ALMA in the submillimeter, we only see molecules in one of the two components. But when we observe the same system at lower frequencies with the VLA, we see molecular emission appearing also in the second component. So this means that in the submillimeter, we are completely blind to the molecular emission because of the high dust opacity. The other famous example is the disk in the young protostar HH212. And in this case, we see a dark lane in both the continuum and the molecular emission corresponding to the disk midplane. Also, in this case, we don't know if the molecules are not there or simply we cannot see them because of the high dust opacity. So moving at lower frequency will mitigate this problem. And there is also a second advantage. This is a simple simulation to show you two molecules, HC11N and the HC13N. And you can see that with the same temperature and column density, as soon as you increase the complexity, the emission peak moves to the left. So this means that large molecules have their emission peak at lower frequency, and we really need to go at radio frequency if we want to observe them. For this reason, we decided to perform a pilot study using the Green Bank telescope for a total of 53 hours observed. And the first step was a survey in the Ku band, so between 14 and 15.5 gigahertz, of two objects, L1544, which is the prototype of a prestellar core, and IRAS16293-2422, which is the prototype of a sun-like protostars. Both these objects are very well studied in the sub-millimeter, and they show a rich chemistry with emission from relatively simple carbon chains, cyanopolyeins, and interstellar complex organic molecules. Since the spectra of L1544 were particularly rich in the Ku band, we decided to follow up these objects with a survey also in the X band. We detected many species, and you can already see from a first look that the spectra of the two objects show significant differences. In particular, in IRAS16293, we only detect C3H emission from the envelope and formaldehyde coming from the protostar, while in L1544 we detected many cyanopolyeins and all these carbon-bearing species. This is not due to the beam dilution, because it is true that the emission from the protostar can be diluted in the big Green Bank telescope beam, but the molecular cloud containing IRAS16293 fills the beam. So there is a real chemical diversity between this molecular cloud containing IRAS16293 and L1544. As a first step, we focused on the cyanopolyein emission in L1544. So we detected bright emission lines from HC3N, HC5N, HC7N, and HC9N, which was detected for the first time toward the source. We performed a non-LT large velocity gradient analysis, fitting simultaneously all the species, thanks to new collisional coefficient estimates. The results of this analysis, in addition to the high spectral resolution provided by the Green Bank telescope, allowed us to determine that the bulk of the emission is coming from the outer layers of the core, and in particular from this redshifted peak, which corresponds to the southern part of the core, which is more exposed to the UV interstellar field. So these results are important because they show that a complex carbon chemistry is active in L1544, and it may be triggered by the UV field, which extract free carbon from the CO and make it available to form these carbon chains. We have still few sources in which these complex carbon species are observed. You can see here in the plot that we have few observations of HC5N and HC7N, and very few of HC9N. The derived column densities are consistent with what we derive in L1544. But in any case, in the last few years, a huge effort has been done to explore carbon chains and rings in star-forming regions. So in particular, TMC1, another dark core, has been the target of two surveys, the Gotham and the Quixote survey, with the Green Bank telescope and the Yebes 14-meter telescope. And these surveys have revealed a new chemical complexity with the detection of several species, in some cases for the first time in the ISM, such as the indene benzonitrile and these other species. And the iCOMs survey includes observation in other 4 prestellar cores, and the detection of benzonitrile seems to show that this aromatic chemistry is widespread, despite not yet considered in the current chemical models. So our observations are fundamental to start to do comparison between the chemistry of different sources and to investigate the complex carbon species formation process. To summarize, we surveyed with the Green Bank telescope L1544, the prototypical prestellar core, and IRAS16293, the prototype of solar-type protostars at large spatial scales, and we observed differences in the chemistry. So the first one is rich in cyanopolyions and heavy carbon chains, while the second one is not. Thanks to this observation, we start to investigate the origin of these differences, which could be related either to a different external irradiation or to evolutionary or environmental effects. Of course, the main limitation is that with the current facilities, we cannot observe the inner regions of sun-like protostars. Because the compact emission would be too much beam diluted in the GBT beam. In the next years, with ngVLA and SKA, we will be able to study the small spatial scales. And in particular, the detection and study of large molecules in planet-forming regions are among the main objectives of both ngVLA and SKA, and several science cases have been developed in the framework of the Cradle of Life working groups. And more specifically, this pilot project inspired a new SKA user case dedicated to the exploration of heavy carbon species in a star-forming region representative of our solar system Earth environment. We propose to observe OMC2 because with the large SKA beam, we will cover several protostellar regions, including the OMC2 far-infrared 4 protocluster, which is particularly interesting for its chemistry. We propose to observe this cluster at an angular resolution down to 0.5 arc seconds, which will correspond to the inner 200 AU. And this region has the advantage of being very well studied in the sub-millimeter, so that we have a good estimate of the energetic particle flux in the different part of the region. So this will allow us not only to detect for the first time complex carbon species, but also to investigate in detail their formation and destruction mechanism. Thanks a lot for your attention. Hello.
Okay. Oops. I don't know what that was. Oh, okay. Thank you. Questions for the speaker. So I guess there is a question online. So the microphone for Kim, please.
Mumma Charnley asks, I may have missed it, but can you define what you mean by low frequencies? What frequency range are you considering here?
Yes, the frequency ranges covered by the Green Bank was the KU band and the X band, so around 8 and 15 gigahertz, more or less.
Questions? Over there, in the back.
Hi, so it's not entirely my field. So I was wondering, because you talk of finding a representative for solar system formation. So are we specifically talking, for example, about the sun? Because that formed 4.6 billion years ago. So how do we know that it's representative? Or are we talking more general?
In the case of OMC2 far-infrared 4, it seems more representative because it's a protocluster, so it's a crowded environment in which several stars are forming, and in particular there are some evidence that it is permeated by a flux of high energetic particles. And this seems also the case of the solar system, because we have indications of short-lived radionuclides in meteoritic material. So we can, there are some indications that show that the sun is not born in a quiet environment, but in a quite energetic environment. That's why Orion may be more representative of this environment.
Other questions? So let me ask one. So how far are we from having a chemical model that would be predictive for this type of molecules? And what do we need to do to get there?
We are quite far because many of the molecular reactions that are used in the actual molecular codes are not studied either in the laboratory or in with quantum chemistry theoretical calculation. And some of them are simply wrong. So it's very time consuming to test the efficiency of all these different molecular species. There is a huge effort of the community in this sense to review the chemical reactions, but I think we are still quite far from having a complete view.
Okay, yeah, quite an opportunity for newer people. Good, so I think we're going to thank Eleonora again and move to the very, very last talk.
Thank you.